In the text in this chapter, I explained that there are two methods for obtaining the Frobenius norm of a matrix. One method is to take all the individual elements of the matrix, square them, sum them up, and take the square root. The other method is called the trace method, and that works by computing the trace, which is the sum of all the diagonal elements of A transpose A, and then also taking the square root of the trace. So, two different methods. I hope I explained clearly enough in the text, in the chapter, why those two methods are the same. But it's always nice to have an empirical confirmation. And of course, this is a great excuse to continue working with linear algebra in Python, in particular using NumPy. Okay, so what you want to do in exercise 3 here is to demonstrate that the trace method and the element-wise method produce the same result. And then I ask whether that only works for A transpose A, or whether you get the same result for A times A transpose. Okay, so now I will switch to Python and I'll show you my solution. So here I'm creating a matrix. It's a nice big matrix, 50 by 50, all of random numbers. Of course, this has to be a square matrix because we want to take the trace, and the trace is defined only for square matrices. Okay, so here I call this norm 1 and norm 2. This is the Euclidean norm method. So here I'm taking all the individual elements, squaring them, summing them, and taking the square root. And here is the trace method where I take A transpose times A and then take the diagonal elements, so only the diagonal elements, ignoring all the off-diagonal elements, sum the diagonal elements, that's the trace, and then take the square root of that. Okay, and if these two methods are equal, their difference should be, in theory, 0, but we will accept some number that's very, very close to 0. Let's consider this to be a number that's very, very close to 0. Okay, now, we can run this multiple times. Oh, there we get exactly 0, which is great. It's pretty impressive to find two different methods, numerical methods, that give exactly the same result, 0.00000, with such a huge matrix. So that is an empirical confirmation that these two methods produce the same result. And now the second thing I asked was about whether it also works for A times A transpose, or also in addition to A transpose times A. And, well, you won't be surprised to see that, yes, indeed, it works for the matrix times its transpose. It doesn't matter the order. Obviously, the order does matter for many kinds of operations in matrix arithmetic, but there are exceptions. There are cases where you can multiply a matrix by its transpose on either side, and the result is going to be the same. The trace method for computing the Euclidean norm of a matrix is one of those exceptions.